welcome back. This is lecture 24. So up until now we have been discussing about fairly detailed way of dealing with noise, right? Thermal noise. And then we started discussing about distortion. Without even me spelling it out, you probably would recognize the fact that the amount of noise determines the minimum amount of signal that you must have in order to make sense of it, right? So noise determines the sensitivity of your receiver, right? So you need to have a signal above that noise level to make sense of the signal, else you will always get some random junk and you will not be able to make sense of what it is. And what is the role of distortion? Distortion essentially gives you the maximum amount of signal that you can have or you can tolerate without it getting corrupted with other distorted versions of the signal, right? So in one way, one of the noise determines the minimum level and the distortion determines the maximum level, right? So intuitively or qualitatively we understand this, but is there a way to mathematically form a framework which says that this is the range of signal between the maximum and the minimum that is tolerable? I mean, intuitively you also understand that the lower the noise floor, more will be the range, and maybe if the distortion is smaller, or rather if I say the IIP3 is more, right, then the range will again be the maximum signal handling capacity of my system will be better, right? So if the noise is smaller, the floor is smaller, and the IIP3 is larger, or either of these two, then I understand that the system is a better system in handling signals, right? What is the formal way of understanding what is that range? And that is what we are going to discuss in the next few minutes now, right? So we understand that noise determines the minimum signal level, right? And it need not necessarily be the signal has to be exactly equal to the noise, but maybe some factor more than the noise, but at least we know that the noise determines the minimum level, right? And let me just say distortion determines the maximum signal level, right? So if we agree with this, with these two assertions, then the next thing is to quantify it or develop a mathematical framework as to determine how good or what that a system is based on the difference of distortion and noise, right? So that's what that's what we are going to do next, right? So in order to do that, so what I'll do is I will draw a graph of where x-axis is the input power to the system, right, P in, and I will plot it in dBm, and y-axis is E out, again in dBm. Okay, and we understand that the system always has some noise, right? Let's say there is some amount of integrated noise within the band, which is essentially determining the sensitivity of my system, right? So noise plus noise, if in dBm, it's basically the noise floor, right, minus 174 plus 10 log the bandwidth, right? At room temperature, you do that, so then you get some integrated noise, which is essentially the sensitivity, right? So let's call that noise, the output noise, to be and times gain, right? So if I'm talking about output noise, then I need to have a gain also, right? So let's say this is the noise output in dBm. Right, this is output noise floor. So clearly, when you are observing, if this is your system, this is your input, and this is your output. Here you are getting, what are you getting? You are getting noise, and you are getting P out. In P out you are getting fundamental, and you are getting distortion. And if I limit myself to only third order component, right? Why third order component? Because we know that second order components can probably be cancelled out by taking differential and all those things, right? So the next thing to tackle is a third order component. So if I only limit myself to third order component, then I'm going to have IM3, right? So I understand that at the output side, I'm going to have a desired fundamental, and I'm going to have an undesired noise, and I'm going to have an undesired IM3, right? Okay. So when I'm observing, let's run a hypothetical experiment where P in is extremely small. It is so small that at the output you only see noise, right? So then what is that scenario? In that scenario, the P out is probably, the fundamental of the P out is probably well below the noise floor, right? So the fundamental of the P out is well below the noise floor. Okay, so maybe your P out is somewhere here, right? And what am I doing? The experiment that I'm going to run is I'm going to sweep the input power. If I'm sweeping the input power, the output power will also increase at the rate of, the fundamental of the output power will also increase at the rate of 1 dB per dB, right? Okay. So the fundamental of the output power is also going to increase by 1 dB per dB, and eventually it is going to come up over noise floor, and it is going to keep on increasing, right? Ideally it is going to keep on increasing, but in reality, no. We'll talk about that a bit later. But let's assume it keeps on increasing. Now, what about the IM3 term? So the IM3 term for a weakly nonlinear system will be much smaller than the, at least at lower power levels, will be much smaller than the fundamental term, right? So an IM3 term will probably be coming from, we'll have a 3 dB per decade slope, but will probably be something like this, right? Okay. So now note that, let's say I am at a power level, input power level of somewhere here, right, where I see the output power, the output to be some power here, right? But would I observe at the output any tone correspond to IM3? Clearly no, because the tone is below the noise floor, correct? So now I keep on increasing the P in. So what's going to happen? Your IM3 tone is also going to increase, right? And eventually it is going to come above noise floor, right? So if you do the experiment, you are not going to see any IM3, you are not going to see any IM3. You keep on increasing the P in, and suddenly a tone of IM3 is going to emerge out of the noise floor, right? So you know that beyond that, if I keep increasing the input power, this IM3 tone will keep on increasing, right? So now you know that. So, and now you know that the maximum amount of input power for which the IM3 becomes visible is that value of P in, right? So essentially, so if I say that this is that P in critical. So if I say that this is the critical value of P in for which I get some P out, correct? So for this critical value of P in, I get some P out such that if I increase P in from that level, I am also going to start to see IM3. And if I am reducing, if I am working below this P in, I am not going to see the IM3, but the difference between the signal and the noise will be not as much, right? So ultimately, what do I want? We want to ensure that the signal power is sufficiently away from the noise power, right? So I want to operate at as high a signal power as possible with respect to noise, so that I can discern, I can have high signal to noise ratio, right? But if in that pursuit of getting high signal to noise ratio, if I keep increasing the signal, I will see that I'll also start getting IM3. So the maximum power at which you do not start, the maximum power at which you start to see IM3, right? At the threshold where you start to see IM3 is the one that I am targeting. And let's assume that is that I have, and this P in critical is that power level, right? So if that is the case, then the difference between this the output power, so this difference, we call it as there's a name for this, it's called the spurious free dynamic range, right? Or this is called the SFDR. Okay, so SFDR is basically spurious free dynamic range. So the reason it is named like that is, moment you have an additional tone with respect, when you apply an input, that tone is often called a spurious tone. In short, it's called a spur, right? So hence, this is the maximum dynamic range. By dynamic range, I mean the difference between the maximum signal output and the noise, right? So that ratio in linear scale, or the difference in dB scale, is a dynamic range. And what is the maximum dynamic range that you can have without having any IM3 tone? We call it the SFDR, or the spurious free dynamic range, right? So the goal of the next 5 minutes is to quantify this SFDR in terms of the known quantities. That is, I want to quantify SFDR with respect to the noise and IIP3 or OIP3, right? So that's what we are going to do. So let's, now that hopefully the motivation is clear, let's go ahead and do that. So that is, once we know that, then this is simple geometry. So let's quickly finish this off. So this is my 1 dB per dB line. Right, and let's say this is that noise floor. This is the integrated output noise, right? And let's say this is my IM3, the strength of the IM3 tone. Let's say this is that IM3 tone, the extrapolated IM3 tone. What am I looking for? This is the part that I'm looking for is what is the SFDR? So this is the SFDR. So the maximum output power for which I do not have any tone. The tone is below the noise floor. Tone is always there, just that it's not visible. It is below the noise floor, right? Okay. So this is my SFDR. Now what do I know? So I know that this point where the red line meets the black line, right? So this is the 1 dB per dB line, and this is the 3 dB per dB line. Where the red line meets the black line is we call it the OIP3, right? Okay. Okay. Fine. And so basically the goal is to find out SFDR in terms of OIP3 and N0. Okay. Okay. So let's see. Fortunately, I know that this triangle, the base and the height are equal because the hypotenuse is at 45 degree, right? It's 1 dB per dB. By the way, everything is in dB. So we get clean linear lines. So the hypotenuse is 45 degree. I know that the base is equal to the height. So I know that this is also equal to SFDR. Right? So this is SFDR. So let me just remove these 3 dB, 1 dB thing to you understand this is 3 dB, that is 1 dB. Let me write it here. Okay. So now, so what am I interested in? I am interested in finding out SFDR in terms of these known parameters, that is N0 and OIP3 and IIP3 and so on, right? So what can I see? I understand that this is SFDR. So how can I express OIP3 in terms of SFDR and N0? I see that OIP3 is, so this is OIP3, right? And this is N0 and SFDR is marked. So basically OIP3 is equal to N0 plus SFDR plus there is a gap, right? So this gap, delta P0, correct? Okay, but I also know that, so let me put it aside. But I also know, what do I know? I know that, use a different color. This height is what? This height is OIP3 minus N0, right? And because this 1 dB per dB line has a 45 degree angle, so which means that I know that this is also equal to OIP3 minus N0, right? So this is also equal to OIP3 minus N0, right? Okay. So what am I left with? So I know that SFDR is equal to, if I, so let's forget about this one for the time being. I know that from this plot, from the horizontal plot, I understand that SFDR is equal to OIP3 minus N0 minus this gap, right? Minus this gap, right? So what is this gap? This gap is same as the delta P0, right? So forget about the delta P0, but we have to find out what does this gap signify. So if I call this delta Pi, right? Now what does this gap signify? Now note that the triangles that are formed by the 45 degree 1 dB per dB line and the 3 dB per dB line, the hypotenuses have a slope of 1 with, I mean, they have the ratio of their slopes is 1:3, right? So which essentially means that this guy is 1/3, right? This guy is 1/3 of the entire range, right? So which essentially means that delta Pi is 1/3 of this entire range, which is YP3 minus N0. So whatever I used, I have basically used this property of the triangle. I mean, the basic trigonometric trick. This is not to the scale, but you get the idea. The slope of right. So because if I call this H and I call this B1 and I call this B2, right? So slope is 1/3, which essentially means that I know that H by B1 is equal to H by V2 times 1/3, right? So that's what I have used. So which essentially means that if I plug and play, your SFDR becomes 2/3 OIP3 minus N0, correct? And OIP3 and N0 are referred to the output. If I want to refer to the input, I know that OIP3 is equal to some gain in dB plus IIP3, right? This is in dBm. So again, OIP3 in dBm. Similarly, I also know that N0 in dBm is gain plus input referred noise in dBm, which essentially means that SFDR can also be expressed as 2/3 IIP3 minus Ni, right? Note that individually IIP3 and your noise changes when you refer it back to the input by the factor of gain, but SFDR does not change, right? SFDR at the output and SFDR at the input are both the same. Okay, so as you can readily figure out from this, that even though IIP3 is an extrapolated figure, right? It's an extrapolated number because you cannot really measure IIP3. You have to extrapolate it because otherwise so many other dominant terms are supposed to come in, that so many other non-dominant terms can come in and they can impact the slopes of 3 dB per dB or 1 dB per dB lines. So you cannot actually give inputs, input tones which correspond to this number IIP3, but you can you will have to give some smaller values of tones and keep and then extrapolate, right? So even though it's an extrapolated number, you see it has a practical significance, and the practical significance is with regards to finding out the range for which you can get the maximum, you can deal with the maximum amount of input, right? Input range for which you do not have a spur and you have the maximum signal to noise ratio, right? So easy way to think about this is what is the maximum signal to noise ratio that you can have without incurring any. So now that we have a basic understanding of IIP3 and SFDR, let me spend a couple more minutes on motivating some other metrics from other metrics which are commonly used in RF terms, which we'll encounter in research papers or even in data sheets, which relates to IIP3 also. So what is essentially IIP3? What did I learn? Well, essentially learned that, so let's say I have a band, I have a signal band, and I have one tone here, and I have maybe another tone. We call this, let's say, omega 1, this is omega 2, right? And if your system is nonlinear, right, this omega 1 and omega 2 is going to mix due to the existence of the third order term, and it will create 2 omega 1 minus omega 2. And if omega 1 and omega 2 are nearby, then naturally 2 omega 1 minus omega 2 is also nearby to omega 1 and omega 2. So you are going to get terms here, and you are going to get some term here. So this is 2 omega 1 minus omega 2, and this is a 2 omega 2 minus omega 1, and they give rise to distortion, right? And when the IM3 components, when we extrapolate the IM3 components because of these, so these are like IM3 components, intermodulation component 3, and if we increase the power and we also increase the that will naturally increase the fundamental and also the IM3, and if we do that, we see that there is intercept, and that intercept we call it as IIP3. Now when the two tones are inside the band is one scenario. It is quite possible that you can have two tones outside the band also. For example, there is a neighboring band. This is my band, right? And this is a neighboring band. Maybe this is a neighboring band. So from here to here, let's say I say this is a neighboring, right? So if there is a neighboring band, which means there is a transmitter maybe next to me, and they are sending out tones, very strong tones outside my band, but pretty strong in their strength, right? So because of the attenuation of my band, because of the attenuation that I am going to have, obviously these tones are going to get attenuated, no doubt about that. But since my LNA is also distorted, right? So it is still going to see some swing. It is still going to get. It is still going to create tones, albeit the strength of the tones will be not as much because of the suppression that these neighboring tones are undergoing, right? So because of this, let's say call this omega 1 out of band, and this is omega 2 out of band, right? So if that is the case, it is going to create tones which can fall here and which can fall here, right? But if this omega 1 out of band and omega 2 out of band are optimally separated, right? Maybe not here, but they are maybe separated in such a way, maybe one is here, other is here. It is quite possible that these two interact and create a tone, one of which can fall here, right? So this is an in-band tone. This is an in-band this IM3. This IM3 is caused by the tones arising out of band signals, right? So when you do this, you are going to see a tone because of this, and naturally moment you have an IM3, you can extrapolate and find out an IIP3 number, right? And the IIP3 that you get after extrapolating this is called out of band IIP3, right? So this is called the IIP3 thus obtained is called out of band IIP3, right? Similarly, in this case, this IIP3 is called in band IIP3 or IB IIP3. Okay, make sense? Okay, so there is another metric of interest that is often used in order to characterize distortion, and that is that does not use two tones, that still uses single tone. But now that we have gone through multiple trigonometric identities, so you should be able to appreciate it quickly. So let's say I have a block, I have a signal, a nonlinear block, and input is Vi, which is Vp cosine omega naught t, and it has a third order nonlinearity, right? So third order. So your output is, let's say, assume to be A1 Vi plus A3 VIQ. So what will be your V naught if input is Vp cosine omega naught t? Your V naught will be A1 Vp cosine omega naught t, which is not a surprise, but you are going to have A3 Vp cube is cosine cube omega naught t. So I can break this up into 1/4 A3 remains 3 cosine omega naught t plus cosine 3 omega naught t, right? So clearly this 3 omega naught t is out of band. It will get filtered out because my RF is a narrow band. It's anyway narrow band. So but the thing is that I am getting an additional term which is in band. Now, so far we have been neglecting this in band stuff, saying that fundamental is much stronger. But now we are going to observe this and try to figure out what is this impact on the fundamental, right? So my in band, so in band strength, so total in band strength therefore is A1 Vp cosine omega naught t plus A3 by 4 cosine omega naught t, right? Now, in order to understand the effect of this A3 by 4 cosine omega naught t, we need to have a physical intuition about what A3 is, right? So what do you think from your basic knowledge of analog circuit? Can you predict whether the sign of A3, will it be a positive sign or will it be a negative sign? So think of it in this way. If I have to model V0 as a weak nonlinearity, A1 Vi plus A3 Vi cube, if A3 is positive, what will Vi versus V0 look like? So this is Vi, V0. If I am only taking the term A1 Vi, then clearly this is going to go on forever on either side. And if I am taking A3 Vi cube, right, if I am taking this, if I am plotting A3 Vi cube and I assume A3 to be positive, right, so then for positive value of Vi, this guy will rise, right? Initially obviously it is going to lag the linear term, but after that it is going to rise. If for the Vi negative, it is going to fall, right? So if I add these two, linear and these two, then you see that it is expanding nonlinearity, right? But what is one of the sources of nonlinearity is because we have limited headroom, right? If we have limited headroom, then obviously it doesn't make sense that I increase Vi, V0 will also increase, right? So because we have a limited headroom, the intuition tells us that A3 will be negative, because ultimately if I keep on increasing Vi, V0 should not increase, the rate of change of V0 should not increase as I keep on increasing Vi, right? Because ultimately I am limited by supply. So, right, ultimately I know that everything will be something like this, right? So, if I have to model transfer characteristics using only A1 and A3, then it makes sense to intuit that A3 has to be negative, right? So, which means that, so for compressive nonlinearity, A3 is less than 0, right? So therefore, what do you see? If I plot this in-band strength with respect to, so by the way, this also times Vp, I missed the Vp, right? So if I plot the fundamental strength with respect to input power, right? So input power in dBm again. So what are you going to see? So clearly at very low input power, when A3 is much less than A1, right, you are going to see, 1 dB per dB slope, right? So 1 dB per dB when A3 by 4, sorry, I made another mistake. This should be Vp cube, right? Because this term rises much faster than the other term, right? So when A3 by 4 Vp cube is much less than A1 Vp, so you get 1 dB per dB, right? And when it stops being much lesser, it starts impacting. What is it going to do to this line? It is going to compress it, right? So this line will start compressing and eventually do this, something like this. So if you extrapolate this, 1 dB per dB line, the power at which the compression is 1 dB below wherever it was supposed to be, right? So let's say this is somewhere here. So this is 1 dB. So this power point is called P1 dB, right? Similarly, the output corresponding power is called output P1 dB. Okay, makes sense? So by the way, what does it tell you for a linear circuit? What do you think this P1 dB will be? Will it be on the right hand side? If I'm comparing two circuits, which has identical gain, right? Which is identical gain, but I say one is more linear than the other. So the more linear network will have a P1 dB on the right hand side of the axis with respect to the other or not? Clearly, higher P1 dB means more linear network. But there is slight pitfall here that you cannot compare two networks with P1 dB only if you do not have the value of gain. See, right? Why? The reason is, let's say I have one network. I say that let's have an amplifier which has a gain of G and a P1 dB of, let's say, 0 dBm, right? Which means that for input power of 0 dBm, right? So which means that if input is, let's say, much lower than 0 dBm, let's say minus 20 dBm, my output is supposed to be G plus minus 20 dBm. And if I have minus 19 dBm, output has to be G plus minus 19 dBm. I keep on increasing, but when I suddenly see that I come to 0 dBm, I am expecting what? G plus 0 dBm. But in my observation, I am not getting 0 dBm, G plus 0 dBm. I am getting G plus 0 dBm minus 1 dB. Right? So that's how I know it's a P1 dB of 0 dBm. Right? But let's say now I put an ideal amplifier which does not have any distortion, right? And I do the same experiment again. So what I mean is, let's put a ideal amplifier, which means its P1 dB is infinite, right? And then I put our same amplifier of gain G and having a P1 dB of 0 dBm in front of it, right? After this ideal amplifier of gain, let's say 10 dB, power gain of 10 dB, and let's assume matching and everything is taken care of, so that we don't have to bother too much. Okay, so now what will be the P1 dB of this entire system? If I consider it to be a single block, what will be the P1 dB of the entire system? So note that if I give minus 20 dBm here, what will be the output of the first block? This will be minus 10 dBm. And what am I going to see? I am going to see minus 10 dBm plus G, right? Or rather G plus minus 10 dBm. right? Similarly, once I come to minus 10 dBm, what am I going to see? Here I am going to get 0 dBm, and here what I am going to see at the output, I am going to see, because this is at 0 with 0 dBm input, my P1 dB is what? 0 dBm input for the second block is effectively it's P1 dB, right? So I will get G plus 0 dBm minus 1 dB. So what is the P1 dB block? What is the P1 dB for this entire block? So if this is my entire block, the P1 dB for this entire block is minus 10 dBm. But so this is P1 dB. But does this mean that this setup is worse off than the previous setup? Clearly no. The P1 dB in this case is reduced, because note that P1 dB by definition is input referred, right? Just because I have a very good amplifier which is amplifying the input does not mean that my P1 dB of the entire block the entire system has become worse off, right? So that is why it is not sufficient to only quote P1 dB. You'll have to quote P1 dB plus the gain, or you might want to simply quote the output P1 dB. Note that the output P1 dB doesn't really change for either of these two scenarios, right? Okay. So there is, now that we are at discussing about P1 dB, there is one final thing that, or rather, your 1 dB. This is also called a one. By the way, P1 dB is also called 1 dB compression point. 1 dB. Okay. So there is one more metric that you will find in research papers, that is called blocker 1 dB compression point, and that is as follows. So let's say I have a in-band signal. This is the in-band tone, and I have one tone here which is expected tone, and I have let's say a blocker tone. This is out of band, right? So this is out of band blocker. So I'll not prove this, but you can anticipate that if I do not, so this is in band. So small signal means apply small signal in band input and a out of band blocker. Then keep increasing the out of band blocker strength and observe the output strength of the in-band signal. So the strength of the out of band blocker at which the in-band signal compresses by 1 dB is called B1 dB, right? So what is the intuition behind this compression? I mean, you can always write a bunch of maths to show that, but the intuition is the fact that, so let's say I have an LNA. I mean, consider let's say a common source LNA. Let's say I have a matching in place. Let's say I have forcefully matched it with a resistor, and I have a input, and the input has a the input has a sinusoid of of known frequency of an in-band frequency, and a blocker of a higher frequency, right? A blocker at a higher frequency, which means that maybe something like this, right? Need not necessarily be multiple of the need not necessarily be a multiple frequency need not be a multiple of the in-band frequency. It can be maybe 1.5x higher or something like that. So let's say something like this, right? So what will happen here? What will you see here? At here you are going to see, obviously, if I assume superposition, which I strictly should not assume, but in this case, because because we are around the gate, approximately it's a linear circuit. I can assume it's a linear circuit, and if I assume superposition, I'm going to see some attenuated version of the input and some attenuated version of the signal of the blocker also. Now, what is happening to the overdrive voltage here? The overdrive voltage of the MOSFET is getting modulated by both the signal and the blocker. But if the blocker keeps on getting stronger and stronger, then the overdrive itself, it's quite possible that you are compressing the overdrive of the MOSFET so much that the signal itself doesn't have any way of going through. I mean, that's an extreme scenario, but as you can see that it can happen that because the blocker, even if it's out of band, maybe it has gotten filtered, but even after filtering, it is possible that I keep on increasing the blocker input, blocker power, and based on the blocker power, there will be a certain blocker power for which your MOSFET cannot take it anymore, and it will start compressing the signal, right? That measure is also an important measure to understand the performance of an RF system, and that is often called blocker 1 dB compression point. So again, if you look at research papers, you are going to see these terminologies. Again, I mean, for the purpose of setting up a question based on this, it is difficult, right? But because essentially the source of all of these are the same. But the key thing to note is that when you are designing an RF system which is interfacing with the antenna, right, or even if you have a chain of these blocks which are interfacing with each other, you will have to design keeping all these matrices in mind. And typically in most of these cases, if you keep sufficient amount of headroom, right, then it's a good place to start, right? But having said that, they are not ubiquitous. So what we'll do, we'll stop here, and in the next class we'll wrap up these definitions and tie them together and start giving you some ideas about what are the existing techniques of reducing distortion, right? Okay, we'll stop here.